Okay, so the title of this module is Solving the Systems of Nonlinear Algebraic Equations. And let me start with a very simple version of a nonlinear system, which is not really a system, it's just one polynomial equation. So how to obtain the roots of a polynomial. So I'm aiming at obtaining the roots of this fifth order polynomial. There is a very simple command called roots, but for this command you need to define a vector of coefficients of that polynomial. So if my polynomial is 2 times x to the power of 5 plus 3 times x to the power of 4 and so on, this is how I define my vector of the coefficients. Then I apply the command called roots to that vector, and MATLAB will give me the solutions. So let me show you how that works. Okay, so MATLAB gives me the roots, 5 roots. The degree of the polynomial should be equal to the number of the roots of that polynomial. You can solve the inverse problem if you have a set of roots. Then you can find the polynomial that yields those roots. Every time you make up a set of roots, make sure that this is a so-called self-conjugate set. Self-conjugate means that if you give a complex value, you have to make up a complex conjugate value. So I'm looking for a polynomial that generates the roots such as 2, 2 minus 4, minus 1 plus minus 4i, plus minus 9i, and 0. Okay? Again, this has to be a self-conjugate set, meaning that if you have a complex value, you must have a complex conjugate value. And the command for this is called poly. So you make up a vector of the roots, and then you apply the command poly to this, and MATLAB will give you the vector of the coefficients of the polynomial. So this is going to be like this. So there are 9 9 coefficients in total, because there are 1, 2, 3, 4, 5, 6, 7, 8 roots, and it corresponds to a polynomial with 9 coefficients. Okay, so it's a dual command. So one command is roots, which finds the roots of the polynomial. Another command is called poly, that finds the coefficients of the polynomial that yields the desired roots. So you can verify what you have obtained. So my polynomial, based on the coefficients that are given, my polynomial is going to look like this, and you can verify. So when you take the roots of this polynomial coefficients vector, they have to match up the roots that you have declared earlier, and you can see that they do match. Sometimes you would have to solve the parametrically defined polynomials. Let me show you how to handle this. So let's say I am trying to solve the polynomial a to the times x to the power of 3 plus bx squared plus cx plus d, and all those coefficients a, b, c, and d are varying. So for different values of those parameters, I need to find out the roots of that polynomial. For that structure, you use the nested for loop. So before you need to identify, you need to define the values of each of those parameters. So my a, you define the array of data. So for a is going to run between -3 and 3 with the step 1. Let's say b, I make it up, run from -2 to 3 with the step 1, and you can manipulate the step. You can change the step to be 0.1, 2, whatever is more convenient for you. Whatever is necessary for your problem. Same thing with C, same thing with D. And then you define 4 nested loops. So my internal index I is going to run from 1 to the length of A, J is going to run from 1 to the length of B, and so on. And then you're solving, first of all, you're defining the vector of the coefficients for each selection of A, B, C, and D. And then you apply the roots command. And MATLAB is going to compute the roots every time. So you see, every time it's going to give you 3 roots, because it's a third order polynomial, for each of those values of the parameters. and so on. If only one parameter is changing, you can plot the so-called root locus, which is basically a comprehensive picture of the migration of the polynomial roots depending on the value of the parameter. So let's say, to be more specific, let's say I am looking for the roots of this polynomial where I only have last free term being a varying coefficient. And that varying coefficient runs between -1 and 3 with the step 1. Between -3 and 3 with the step 1. So I'm opening up a for loop. I'm going to define the coefficients of the polynomial. I'm going to find the roots. And I'm going to plot those roots on the figure. How do I do that? I'm extracting the real part, and I'm extracting the imaginary part of those roots. And usually, since you want to distinguish between the beginning of that migration of that root locus and the end of it, typically for the initial value of the root, you mark it up with x. So if that's what I'm saying here, if I is equal to 1, then you're going to plot this real part versus the imaginary part in using the x symbol. And then for everything else, so else, you're going to plot it with the dot. Okay? And don't forget to hold on, because otherwise MATLAB will erase the previous plot and then put a new plot on the top of it. So in order to prevent that, you do the hold on command. You use the hold on command. So that way, when you plot it, it looks something like this. So by x, I marked up the beginning. So for the first value of the parameter a, which was, let me see, it was -3, I mark up my roots as x. Okay, so those are the beginnings. And then as a changes, I'm going to see the migration of the roots of that polynomial, like this. But this is more of a manual way of plotting the so-called root locus. There is a more professional way of plotting it. It's done through the rlocus command. So if you need to do some dynamics problems, like control problems, I suggest that you use the rlocus command. But for other types of problems, when you just need to find out where the roots go depending on the value of the parameter, you can do this sort of a manual thing, which is done through this subroutine. Okay, another example. You can find a zero of a function through the so-called f0 command. So if the roots command looks for the roots of the polynomial, the f0 command looks for the zeros of a scalar function. So f of x is a scalar function of a scalar variable x. It just looks for the zeros of that function, and this is the syntax of this whole thing. Let me comment this one out first. So the syntax for the f0 command is follows. It goes as follows. So you have to specify the function of which you're looking for the zero, and that is done through this string. It's @fun. You can call it any way you want. So MATLAB, once MATLAB sees that, it's going to look for the subroutine called fun, and it's right here. And in this subroutine, you're going to define the function of which you're looking for the zero. So it's sine of x, let's say. So MATLAB knows that it needs to to solve the equation sine of x is equal to 0. You have to give the initial guess for the solution. So we know that sine of x is equal to 0 at 0, but you're given the MATLAB initial guess. And if you run this, so hopefully MATLAB will identify. So it identifies, so every trigonometric equation has multiple solutions. So sine of x is equal to 0 at x equal to 0, but the closest solution to the one that, to my initial guess, 3, was the value of x equal to pi. So MATLAB finds that one. So this is kind of disadvantage. So don't expect MATLAB to find all solutions, especially for nonlinear equations. It's going to find the closest solution to your initial guess. Okay? So this is one of the ways to do that. If you need to specify the interval on which you need to obtain the solution, you can do that as well. So searching for a solution on a given interval. So it's the same function, sine of x is equal, same equation, sine of x is equal to 0, but now you're looking for the solution on the interval between -1 and 1. That's why you are specifying x0 as the interval between -1 and 1. This is going to be your, so MATLAB will select the initial guess on that, within that interval, and hopefully it will end up with the solution that is equal to 0. No. Okay. So MATLAB ends up with still finding the solution at x equal to pi. So as I said, MATLAB is not going to give you the entire array of the solutions. It's going to give you the solution that is that it finds through the iterative procedure. So in this case, it ends up being the same value of pi. Okay. How to solve the systems of nonlinear algebraic equations? For that, you need to define the symbolic variables x, y, and z, and I just made up 3 equations. As you can see, they are nonlinear. It could be done through the solve command. We discussed solve command in the context of systems of linear algebraic equations, but solve command can also help you find solutions to the nonlinear systems, systems of nonlinear algebraic equations. And the approach is the same. So MATLAB-wise is the same routine. So you apply solve to the equations of interest, and in order to extract the solutions, you apply these commands. So let me comment out everything else for now, and just run this piece of code. Okay, so MATLAB gives you the solution for x, y, and z, and then I verify whether this solution is indeed satisfies the equation. So I'm applying, I'm substituting those values for the solution into the equation, and hopefully at the end I should get zeros, and indeed I do. So in MATLAB language, 10 to the power of minus 38 is 0. Same for the second equation, and same for the third equation. Okay, so you verify that it is indeed what you got is indeed the solution. Last piece. I think I briefly mentioned that probably in the previous module that you can apply solve, but you can also apply fsolve command. So the difference between the two is that fsolve in situations when the number of equations is less than the number of variables, the command solve is going to solve this system symbolically, while the fsolve command targets pure exclusively numerical method for solving the system of algebraic equations, whether linear or nonlinear. So for example, let's say I have 2 equations but 3 unknowns. So one unknown could be a free term. The solution to this could be expressed in terms of that free term. So for example, I have these 2 equations, and again they depend on x, y, and z, and I would like to solve these 2 equations with x and y being my unknown variables. So I specify them here, I apply solve command, and my answer should depend on z. So that's the advantage of the solve command. Solve command will solve this system of equations symbolically, and will give you the answer symbolically, like this and like this for x and for y. Fsolve command is not applicable in this case, so you don't want to use the fsolve command in this situation. You can solve, this is an example of using fsolve command for a nonlinear system of equations. The advantage or disadvantage of one command versus another could be judged by the time that it takes, especially in some big algebraic equations. So one command could be more advantageous versus the other. For example, maybe fsolve could be more numerically advantageous than as opposed to solve command, because the solve command tries to solve the system symbolically as opposed to numerically. But this is an example of how you use the fsolve command. It's very simple, very similar to the one that we have discussed earlier, which is called f0. So the syntax is very similar. So I am solving this system of equations, of algebraic equations, but nonlinear equations. Okay, so each of those equations has to be equal to 0, and that's what I'm trying to solve. I'm applying the fsolve command. So fsolve is trying to solve the system of equations which is defined in the subroutine called fun. You can call it any way you want. I call it fun, function, or equations. You can call it any way you want. So, but as long as MATLAB sees this fun, it's going to look for the subroutine called fun. This is how I define my subroutine. I type up function. You can give that function a name, let's say G, and make sure you call it fun. In the brackets, you specify the variable, the unknown. It's going to be a vector of unknowns, x. X is going to have, given the fact that we have 3 equations and 3 unknowns, x is going to have 3 components, x1, x2, and x3, which are present in all these 3 equations. So MATLAB is going to solve this iteratively, every time calling up this subroutine called fun, until it hits the value of these expressions close enough to 0 within the limit of tolerance. So basically this is the structure. If you run this, MATLAB will give you not only the solution right here, but also the value of the equations themselves, just to verify that you indeed got the solution. So you can see that the value of the expression on the left-hand side of the equation, which is supposed to be 0, here is very close to 0, 10 to the power of minus 11. In MATLAB language, it is viewed as 0. Okay, so this is how you implement the fsolve command. And my next example is how to use fsolve command to solve the parametrically defined systems of equations. So we're going to capitalize on everything we have discussed earlier. So here's my system. I have a parameter A, which could be changing. So I'm going to solve this system for various values of the parameter A. So what do I need for this? I need my initial guess. I'll just leave it as the way it was before. I'll come back to this global thing in a second. My parameter A is going to change between -4 and 4 with the step 2. Again, this is a user-defined string of values, so it's up to you, whatever your problem calls you to do. You're going to open up the for loop, and within this for loop, you're going to apply the fsolve command, and the system of equations is going to be defined in the subroutine that I call fun1. So MATLAB is going to, every time MATLAB is going to look for fun1, where I define the variable, the equations. So that when MATLAB comes to this subroutine called fun1, it needs to know the value of the parameter a sub I. Okay? For this, I need to define a and I index as global variables. The advantage of declaring something as a global variable means that when MATLAB jumps from one subroutine to another subroutine, and by subroutine I mean this function, what I call here h, and function v, those are called subroutines. So when MATLAB jumps between them, so that it knows the values of certain parameters. So if I define the value of a in subroutine h and the value of I in subroutine h, in order for MATLAB to know their value in a different subroutine, I define them as global variables, as global parameters. So when I'd have to type up global here and global here. That way MATLAB will know the value of a sub I at each step of the for loop cycle. So you can make it run like this. So every time, so the parameter a is going to have -4, -2, 0, 2, 4, 5 values. So for loop is going to run 5 times, and it's going to give me 5 solutions. And every time it gives me a solution, it also verifies whether the left-hand side of the equation is indeed 0. And you can see that 10 to the power of minus 10 is viewed to be a 0. So I got 5 solutions for 5 different parameters. This is how you solve nonlinear algebraic equations that are parametrically defined, which means that there is a parameter that takes several values, and for each value you need to solve that system of equations. This is the structure that you need to use in order to handle any kinds of projects. I want to show you some interesting thing. Let me see. Let me comment this, and let me open up this. So what I do here, I'm solving the exact same thing. Nothing has changed except that I'm plotting the solution versus the parameter. So in some of the assignments, you might have to solve the system of algebraic equations and then show how the roots, or not the roots, solutions to this system of equations change with the changing of the parameter. How to make that plot. So this is how you do this. I'm just, since I commented out this part, I'm going to have to rewrite everything here. So I define my A. I'm going to solve my system of equations, same system of equations, but every time I solve this, I am going to, let's say, extract the first solution to this system, and I'm going to build an array of data that correspond to each value of the parameter. This is how I do that. So I define an empty vector initially, and then I'm going to augment this empty vector with the current value of the first solution to my system. And then once the for loop has run, I'm going to end up with x1, the vector called x1, which contains the values of the first solution for each value of the parameter a. And that way I can eventually plot it like this. So if you run it, you will see that how that solution migrates with the change of a. So on the horizontal axis I have a, on the vertical axis I have the root. And this is the plot. Okay? So it's just an alternative, not the alternative, it's an augmentation to the previous problem where in addition, you also plot the migration of the solution with respect to the parameter a. And that completes this module.